Good evening, everyone. Welcome to the NPTEL Symmetry and Group Theory Interactive Session 4. My name is Tanu Kaushik, and today we will be discussing about groups and its properties, and we will be studying how to classify the symmetry operations in a class and what are their applications further. So let's begin with the our fourth interactive session. So we will be starting with groups and its properties. So what is a group? Group is basically a combination of symmetry operations associated with some important rules and properties. And we will be looking into the properties it follows and how they rule into forming certain groups with different symmetry operations for a certain molecule. So, group is a combination of symmetry operations associated with some important rules and properties. So we also we know we generally say that this molecule falls into this point group and like H2O falls into C2V point group, NSC falls into C3V point group. So basically group is also known as point group because during the application of operation, one point within the molecule always remains unshifted. For example, if when we are performing the operations in H2O, generally the oxygen atoms remain unshifted or its position or its it remains unshifted throughout the operations. So that's why we call it as a point group. So as during the application application of operation, generally one atom of the molecule will always remain unshifted. So so we will be basically carrying out all the symmetry operations around that static point only. So you must be, you might remember that when we put all the atoms in a molecule in a three-axis system, like three coordinate system, so we generally fix one of the points and we give it as the origin, and we generally give that point, fix that point as origin, which remains unshifted throughout the operation. So we have to take care that all the symmetry operations will be carried around that static point. around that static. So the symmetry operations of a group are associated with four rules. And what are these four rules? Of a group are associated with, and these four rules are closure property. First is closure property, second is identity element, third is associative law. So these rules and these basics have already been discussed in the main sessions by Professor Jitendra Chuk. Here I am just revising it, and I will be taking the examples of groups only here, because there some basic examples were discussed, but here we will be taking like water or some other examples. So I hope you will get a better idea with these examples. Associative law, inverse, inverse law. So let us discuss our first rule, which is closure property. It says that the product of any two element in the group and square of each element must be an element of the same group. What is what is it? I will be showing it with the help of an example. So the product of any two elements in the group and square of each element must be an element of the group. Please think. Okay. So let us take an example now. We are taking water. So just label the hydrogen atoms here. Okay. So what are the symmetry operations present? Like in which point group this H2O falls into? So it comes under C2V point group. And the symmetry operations are E, twofold axis of rotation, sigma xg plane, and sigma yg plane. So let me represent them. So this is the C2 axis of rotation. Then sigma yg plane. I'm taking this as this has z axis. Okay. So this is the sigma yg plane, and the molecular plane of the atom is sigma xg plane. So the coordinate system will look like this for this representation. Okay, so we will be taking two symmetry operations, sigma xt and sigma yg, and we will show how the product of these two operations will give an operation which will also fall into this same group. So let us see how it proves this rule, how it obeys this rule. First we will apply sigma xt. So sigma xt is molecular plane. Okay, this is the molecular plane sigma xt as I have shown into the coordinate system. Okay, so what will be the changes induced in after this reflection? So the atoms will remain on the same positions and there will be no changes induced in this system. So it will remain like this. Now let us follow next symmetry operation, that is sigma yg on this system. So now sigma yg is like this reflection having C2 axis of rotation on it. So it will give us this configuration. So now can you see which symmetry operation will can directly give us like just label this configuration as first, second, third. So which of the symmetry operation in the C2V point group can give the same configuration as we got from moving from first to third after applying this sigma xg operation followed by sigma yg operation. So we can clearly see that C2, if we apply the C2 axis of rotation on this molecule, on this water molecule, then we will get these configurations. So this is the same as third. These both are same configuration. So we can say that sigma yg into sigma xg give us C2 or symmetry operation. So I'm writing it as this, that sigma xg will be applied first, then sigma yg will be applied. Okay. So here we can see that this C2 axis of rotation, this also falls into the same group. So this shows that it obeys the closure property of the uh, group. So we can also show it with some other example, like in the water itself. Again, labeling the atoms. Now we will be seeing a product of C2 and sigma xg. So we will be applying sigma xg first. Now sigma xg is the molecular plane, so we will get the exact similar configuration because it will be bisecting the atoms into half. Okay, it will not be kind of giving a reflection of these atoms. it is passing, this plane is kind of passing through the atom. Now we will be applying next is C2 axis of rotation. So how will it look? So now the configuration will change, and it will, and the position of atoms will be interchanged. So this is the first configuration, this is second, and this is third. So if we have to go directly from first to third, so what is one symmetry operation that can give us same configuration, that is this third configuration from first? That will be definitely sigma yz. So we can say now that sigma xg into C2 is equal to sigma yz. So the product of two operations C2 and sigma xg gave us sigma yz, which is also a part of the group. So all the operations, like all the symmetry elements, all the operations in this point group follows the product of two elements, which we have taken sigma xg, sigma yz, and C2, and they fall into the same group only. And with the help of with the help of this tool, we can create a group multiplication table. Okay, table using these rules. Let's see how it helps us in creating a group multiplication table for C2V point group. So we have symmetry operations, symmetry elements E, C2, sigma xg, and sigma yg. We will be representing it both, okay, E, C2, sigma xg, sigma yg. So now taking the product of these elements, let's see what will be the what group multiplication table we will get. So the product of E into E, we will be writing like this operation will be applied first, followed by this operation. Okay, so let's write it E into E. What we will get? We will get E only. If we apply E operation first and C2 operation on it, then what we will get? C2 operation only. And the product of, similarly, the product of sigma xg and E, we will get sigma xg, sigma yg, and similarly on this axis, we will get C2 axis of rotation, sigma xg and sigma yg. Now, the multiplication of C2 into C2, what will it give? It will give us E operation. Okay. And similarly, sigma xg into sigma xg, it will give E, and sigma yz into sigma yz, it will give us identity element only. So now, in each row and each column, any operation can't be repeated. Okay. So we have already checked that sigma xg into C2, what it is? It is sigma yz. So we got this sigma y. Now only one operation is left, that is sigma xg. So it will take this place. Similarly, here we know now only one position is left. So here we can fill it directly. What can be that? Sigma xg is already there, sigma yz is there, identity element is there. So the only operation left is C2 element. Only element which is left is C2 element. Okay. And in this row again we can put sigma xg. So this way we can fill the directly make a group multiplication table. So this is the group multiplication table for C2V. Now moving to the second rule of a group. And the second rule is identity element. Presence of identity element in a group. So it says there should be one element in the group that must commute with all other elements, remaining them unchanged. Okay, so what does it mean? When we interchange the positions of these two operators, where this one operator will be always fixed, that is, it will always give us the element which will remain unchanged. Clearly writing it, one element in the group must commute with all other elements, remaining them unchanged. And what is that element? That is identity element. So we will always have an identity element, that is E, present in the group. Okay. So now the next rule is, third rule is inverse inverse rule. So what does it say? It says every element in the group must have its reciprocal element present, such that if we multiply an element with its reciprocal, the result will be identity. So if Ax is equal to E, then x is equal to 1 by A, or we can say A inverse, such that A inverse is equal to E. Okay. So now let us take an example to understand this rule. Again, the C2V point group. Next, sigma y. So if we multiply this C2, is C2 into C2 is equal to E sigma xg to sigma xg is equal to E sigma yg to sigma yg is equal to E. So here what we can say that each element is inverse of itself. Is an inverse of itself. And if we like if we multiply C2 into sigma xg, what will we get? We have already seen that C2 into sigma xg will give us sigma yg. C2 into sigma yg will give us sigma xg, sigma xg and into sigma yg will give us C2. So here each element, this shows that each element in this group is an inverse of itself. Not any other element is inverse of other element. Okay, so that we will have to check which element present in the group is an inverse of a certain element. Now I would like to add some basics here. You can mark it. It will be helpful for you in solving uh, assignment problems or any other problems you have. So it is for C and axis. Uh, these two these two axes of rotations will be reciprocal to each other. That is inverse of each other. For example, C31 into C31. It will give us C3 square. But if we multiply C31 into C3 square, it will give us identity element, which means C31 is equal to E into C3 square inverse. Therefore, C31 and C3 square are inverse of each other. Okay. Similarly, for C4, C41, C42, C43, C44. C44 is identity element only. So here we will see that this C41 and C43, C41 and C43 are inverse of each other. Similarly, in C5 axis of rotation, C51, C52, C53, C54. C55 is again identity element. So here this uh, C51 and C54 and C52 and CF3 are inverse of each other. C51 and C54, C52 and C53. So let's move to our next rule, which is associative law. It says that the associative law of multiplication must be followed by the symmetry operations of a group. Associative law of multiplication must be followed by the symmetry operations of a group. Of a group. That is, this is the associative law of multiplication. Uh, so let's again check it with the example of C2V point group. So if we take C2 and the multiplication of sigma xg and sigma yg. So, so it will follow associative law like this. Sigma yg will be outside and this C2 and sigma xg will be in the bracket. So sigma xg into sigma yg, what will it give? It will give us C2 operation. Sigma C2, C2. And similarly, so sigma yg and C2 into sigma xj will give us sigma just a moment, C2 into sigma xg into sigma yg. So C2 into sigma xg will give us C2 only. And the C2 square is equal to E and sigma yg square is equal to E. So all of the elements, all of the operations in a group will follow this associative law. So now let us discuss the properties of a group. first is order of a group. So the total number of symmetry operations present in a group is known as the order of a group, and we have already studied it before, and we have already found out the order of groups for a number of molecules in previous sessions. Of a group is known as order of the group. Representation of a group is order of the group is H. So let us write the point groups and their order. I'm summarizing different point groups and their order in a table. CS CS point group, which has identity element and this sigma plane present only. So its order is to CN point group. So the number of uh, so here it will have identity element and the n-fold axis of rotation present in the group. The order will be n. Then CNV, CNH, DH. So these three point groups will have 2n order. Okay, this is DN. Then DND point group and DNH point group will have 4n 4n point group order. So octahedral point group will have order 48. Tetrahedral group has 24 order. Okay, so this will be the number of total symmetry operations present in a particular group. So I have summarized it here for your convenience. So the second property of the group is classes of a group. So these things will be very helpful for you further in the application of these group multiplication theorems, group multiplication tables in a number of applications. So please practice it and be very good at solving these things for any number of molecules you can get. So please try to solve as number of examples as you can. So what is the classes of a group? It is the classification of symmetry operations. So here basically we will be grouping these symmetry operations in different classes based on certain rules which I will be mentioning here. So why do we classify these symmetry operations? Because symmetry operation of a group can be classified according to their symmetry properties. So the symmetry operations of same symmetry properties will be in the same group, will be in the same class. So those symmetry operations which are giving us similar configurations, or we can say similar results after their operations, we can classify them uh, into one class. And those which are giving different results, we will classify them as individual or into other classes where they are following the similar pattern. So I'm writing it here what exactly it means. Symmetry operation of a group can be classified according to their symmetry properties. The symmetry operation of same symmetry properties will be in the same class. And please note, according to the group theory definition, the similarity transformation elements elements will be in the same class. So now take let us take each of the symmetry operations, and I'll give you certain tips on how can you classify these operations with the help of these basic rules I have seen throughout the examples. So first is we will be seeing in a principal axis of rotation. So the classification of principal axis of rotation. So it says again this C and M and C and n minus M will be in the same class. For example, C3, if we take this C3 principal axis of rotation, then C31 and C32 will be in the same class. And if we take C4 principal axis of rotation and write the operations involved with it, C41, C42, C43, and C44 is again identity element. So here these two operations, C41 and C43, will fall in one class, in same class, and C42 will be another class. So here for C4, we will have two classes. For C4 principal axis of rotation. So I would like to prove it how this C4 like the C41 and C43 will be in the same class, but C42 will be in the different class. Let us see how this property helps us in classifying these symmetry operations. So if I take a molecule which has C4 axis of rotation, let us take Genon OF4. So it will have square pyramidal geometry. And if we apply this C4 one axis of rotation, what will be the configuration we will get? So firstly, I will label the atoms here. And the principal axis of rotation, which is C4, is along xenon and oxygen atom. Okay, so what configuration will it give? So it will give when so it will be changing like this: F1, F2, F3, F. So this is the configuration we get. I'm giving it first and second name. Now, if we move, like if we apply C4 to axis of rotation, that is C4 to what is it? It is basically C2 axis of rotation, if we can say. So what will be the configuration we will get now? So now the atoms will change their positions as this. One, two, three, four. The two-fold axis of rotation. And if we apply, I have done some mistake over here. Let me check it once again. Fine. One, four, three. So this is the C2 axis of rotation or C4 square axis of rotation it has followed. And if we take this C4 3 axis of rotation, what will be the configuration? Let us check. If the configuration will be will get this configuration 1, 2, and 3, 4. Just a minute. So here if you can see the effect of C4 1 and C4 3 is same, that is here 90-degree rotation is happening, but here the configuration is equivalent with C2, that is equivalent to one C2 axis of rotation. So based on this, we classify C4 1 and C4 3 into one class and C4 2 into a different class. This is basically clockwise 90-degree rotation, and this is anti-clockwise 90-degree rotation of the first configuration of xenon OF4. similarly, for we take C5 principal axis of rotation, we will have these operations C51, C52, C53, C54. So C51 and C54 will be in same class, and C52 and C53 will be in same class. There will be two classes for this C5 axis of rotation. Okay, so second is subsidiary C2 axis with different symmetry effects will be in the separate class. So we have seen that there are two different kind of C2 axis of rotation present in a group. So based on that, we can say that subsidiary C2 axis rotation axis with different symmetry effect will be in the separate classes. So let us take some examples. For example, VF3. In VF3, we have three C2 axis of rotation. A subsidiary means where the principal axis of rotation is of higher order and there are C2 axis of rotation associated within that molecule for that particular principal axis of rotation. For example, here VF3 has C3 axis of rotation as its principal axis, and C2 axis is the subsidiary axis of rotation. So this is one C2, another C2, and three C2. So here we have three C2 axis of rotation, but all of the three of them have similar effect. That is, each one of them is passing through bromine and containing one of the fluorine atoms and giving the similar symmetry effect. So these three C2 axes will be in one class only. One class of three C2 axis of rotation. But if we take an example of PTCl4, so here we have two different kind of axis of rotation. So one C2 axis of rotation, one group of C2 axis of rotation is passing through this Cl, platinum and Cl group atoms. Okay, so these two are similar, but there is one more C2 axis of rotation which is passing between the bonds. This is also C2 axis of rotation, and there are two kind of it. So here we will have two C2 axis of two types of C2 axis of rotation. Therefore, we will have two classes of C2 axis of rotation, which we will write as TC2, 2C2 prime and 2C2 double prime. And if we take an example of this, then it has 5 C2 axes passing through each of this each of the carbon atom and bisecting the opposite edge to it. So, so here we have 5 C2, but all of them have similar symmetry effect. So these 5 C2 axes will be in one class. Okay. And if we take an example of benzene, so here we have one C2 axis passing through opposite carbon atoms of the ring, and one C2 axis is cutting the carbon-carbon bonds. So there are two types of C2 axes. So 6 C2, there are total 6 C2 axis of rotation, out of which 3 C2 prime, that is, will be in same class, and if I label it as C2 double prime, same class. Okay. So now moving to the classification of vertical planes. Third is classification of n sigma v planes. Again, vertical planes similar to C2 axis of rotation, vertical planes with similar symmetry effect will be in the same class. Again, taking the example of BF3, it has 3 sigma v planes passing through each of the BF bone. These three bonds have similar effect. Sigma V1, sigma V2, and sigma V3. All these three vertical planes have similar effect. Okay. Therefore, they will be in same class. And if we take this example of PTCl4 again, so here we have one plane having this platinum and two Cl atoms on it. This is one sigma V plane. This is one sigma V two, and there is another plane passing between the bones. This is sigma V double prime one, sigma V two double prime. So basically, these sigma V double prime are dihedral plane because they are cutting two C2 axis, cutting the angle between two C2 axis of rotation. So here we will have two sigma V planes, which are sigma V primes in one class, and two sigma D, which I have mentioned as sigma V double prime in one class. Okay, and if we look into horizontal plane and inversion center, so the horizontal plane and inversion center will be always counted in the separate classes. Okay, because there will be always only one kind of them, and there is no other operation that will give the similar effect. Horizontal plane, sigma h, inversion center, I will be in the separate classes. Okay, next is classification of SN operators. So here again SNM and SNN minus M in proper axis of rotation will be in the same class. Okay, and there is a condition here for abelian groups. What are the abelian groups? Which follows five properties, five rules, which follows, that is closure property, uh, identity element rule, inverse rule, uh, associative law, and commutative law also. So this will follow five properties, unlike other elements, another groups which follows uh, four rules: closure, identity, inverse, and associative law. So these groups, these rules for classification of operations will not be applied. For abelian group, all above classification rules will not be applicable, and therefore each symmetry operation will be in the separate class. So the examples of abelian groups are, which groups are abelian groups? I'm writing it down. Let me check the spelling of this abelian group. I might be writing it wrong. Yeah, so the spelling, please correct the spelling here. Uh, it is Abelian. Similarly here. Okay, so the examples of abelian group are CS, CN, C2V, CNH, D2, and SN. So these groups will be abelian groups, and they will not follow above classification rules that I have mentioned. Okay, above classification rules will be applicable for non-abelian groups only. So now let us take examples of each type of group and see how can we classify the symmetry operations for each of the point group. So let us start with CS point group. So it has two operations, that is identity element and writing it as this. So it has two operations E and sigma, that is one reflection, one plane of symmetry. So it has two operations. Order is 2. So since CS is an abelian group, so each of the symmetry operation for it will be counted as individual class. So here order is 2. So class will be also 2. Okay. Now similarly for group, CN point group, order will be equal to class. Please note for the abelian groups, order will be always equal to class. For abelian groups. So here I take a C2 point group. It will have E and C2 twofold axis of rotation as its principal axis of rotation. It will have only two symmetry operations. So here for it, order is 2 and class is also 2. For C3, the symmetry operations are C31, identity element C31 and C32. So here order is equal to 3 and class will be also 3. Similarly, for C4 point group, it has identity element C41, C42, C43. So it will have order 4 and class will also be 4. Okay. Now let us move to next point group, which is CNV point group. So let us take an example, very common example of C2V point group, S2O. So it has operations E, C2, sigma xg, sigma yg. So here the order is 4 and class will be also 4 because it is also an abelian group, right? And you can check all the properties, closure, inverse, and closure, inverse, identity, associative, and for abelian groups, commutative law also. And you can check if all of these point groups follows these uh, properties of the group or not. Okay, C3V point group, NS3. So it has E, C31, C32, and 3 sigma V. We have already seen like NS3, if we represent it like this, NH, so all of them have almost 120-degree angle between them. I'm representing it like this here. So, and it will have 3 sigma V, each of them passing through each of the NH bonds. Okay, so these 3 sigma V planes have similar effect. So they are in the same class. And C31 and C32 we know have the same effect, so they will also be in the same class. Okay, so if we write them in, in the form of classification into classes, so they will be written as E2C3 and 3 sigma V. So here order, total number of operations we have is 6, but we have class is equal to 3. And also please check, please note that all the point groups that do not have an axis higher than 2 hold excess of rotation are abelian. So let us take next example of C4V point group. Uh, we can take an example of this genome OF4 again. Which is represented like this. Okay, so the symmetry operations of C4V are E, C41, C42, C43, and it has 4 sigma V planes, which are 2 sigma V and 2 sigma D. Okay, so here if we classify them into classes, it will look like this C41 and C43 will be in the same class, 2C4, and this C4 square will be in the separate class. Two vertical planes will be in the same class and two dihedral planes will be in the same class. But all these four vertical planes will not be in the similar class because their symmetry effects are different. So here we can see the order of C4V group is 2, 3, 4, 5, 6, 7, 8. Order is 8, but class is 1, 2, 3, 4, 5. So the class is different here, which is 5. Okay. So here we can also conclude that for CNV point group, if n is even number, then n sigma will be classified into two classes. And if n is odd, then n sigma v will be in the same class. These small tips will be very helpful for you in writing these group multiplication tables. Okay, so please practice them and please note them very carefully. So let us move to next group. Fourth is CNH point group. So this CNH is abelian group. So for any of its example, be it C2H, C3H, C4H, whatever it is, in every case, the order will be this order will always be equal to class. Example C2H point group. It has E, C2, I, and sigma H symmetry operation. So each of these operations have their different symmetry effects. So each of them will be in different classes. So here order is 4. So class will be 4. Okay. If we take another example, it is C3H point group, and we write the symmetry operations in it. C31, C32, sigma H. So here it will have S3 also, S3, 2. So these two will be in the same class and these two will be in the same class. So uh, sorry, here since these are abelian groups, so here this C31 and C32 will not be in the same class. Okay, so these classification rules are not applicable in abelian groups. Next is DN group, DN point group. For DN point group, if n is even, then NC2 will be in two separate classes. And if n is odd, then NC2 will be in the same class. Okay, so just a minute, let me check if the recording is happening or not. Sorry, I haven't zoomed in the screen. Anyway, so let us take some examples here. D2 point group. So it will have C2 as its principal axis of rotation, and it will have two other C2 axis of rotation and one identity element. So it will be written as E C2 C2 prime C2 double prime. So here since n is even, that is n is 2 which is even, so each of the C2 axis of rotation will be in the separate class. So here the order is 4 and class is also 4. And if we take the example of D3, here it has E, C31, C32 and 3C2. So since here n is odd, I have classified these C2 axis of rotation in one class only. So here and this C31 and C32 will also be in the same class. So it will be represented as E2C3 and 3C2. So the order is 6, but class is 3. Okay. Similarly, if we take the example of D5, which has these symmetry operations E, C51, C52, C53, C54, and since n is odd, so there will be nC2 here, that is 5C2. All of them will be in the same class, and these two will be in the same class, and these two will be in the same class. So it will be represented as E2C5, 2C5 prime, and then 5C2. So the order is 10, but the number of class is 4. Okay. So the next point group is D and D point group, which will have following symmetry operations: Cn, principal axis of rotation, n-fold principal axis of rotation, and nC2 axis perpendicular to it, and n sigma v planes associated with it. And it will have S2n improper axis of rotation. Also, if n is even, then I will be absent. I have already taught you this in the last lecture. If n is odd, then I will be present. And the total order will be for these point groups. Total order will be 4n. So here they have these rules. The CNM and Cn and minus m will be in the same class. This SNM, proper axis of rotation, will be again in the same class. Okay. I will always be in the separate class, and this NC2 will always be in the same class. Then n sigma v will be always in the same class. So let us take examples of it. If we take D2D point group, so first we will write the symmetry operations present in this group. We'll have identity element, C2 axis of rotation, 2C2 perpendicular to it, 2 sigma v planes, and S4 axis of improper axis of rotation. So if we classify them here, so I have already taught you identity element will have its separate class. This principal axis of rotation will be in a separate class, and the 2C2, this NC2 will always be in the same class, and again N sigma will be in the same class. But what about this S4 axis of rotation? So let us check. So it will be S41, which is equal to C41 into sigma, S42 is equal to C42 into sigma square. So even power of this sigma will always be identity element, and odd power will give this reflection operation uh, back again. Okay, so S43 will be equal to C43 into sigma. So this will be equal to, and S44 will be equal to C44 into sigma 4. This will be equal to identity element. This is S41. This is C2 or C42, and this is S43. So this won't be counted in a class, and this will be counted in one class, and this will have another one class. So the order is 1, 2, 3, 4, 5, 6, 7, 7, 8, 9. Yeah, order is 8, and the class is 1, 2, 3, 4, 5, 6. Writing, repeating, yeah, I'm counting it again. So the class will be 5. Okay. So in this case, we will always have to look into the different classes being created by this S2N symmetry operation. Okay. Let us take an example of D3 deep point group. So the symmetry operations will be C3, uh, C3 as the principal axis of rotation, 3 C2 axis perpendicular to it, 3 sigma V planes will be present, which will be in the same class. Then S6 will be present, and since N is odd, so we will have this inversion operation and identity element present in the group. So what are the operations being generated by S6? S61, S62, S63, S64, S65, and this S6 into 6 will be E again. So here we will write it as C61 into sigma. It will give S61 only, C62 into sigma square, which is E. I'm writing it as E only, or directly as C62. This will be C63 into sigma, that is S63. This will be uh, C64. This will be S65 only, and S66 is identity element. So these two will be in the same class. These two will be in the same class, and this will make one class. Okay. So from here we are getting three S6, three different classes from S6. But this S63 is equal to S2, which is equal to I. So this is again present already in the group. So it won't be counted as a separate class. So we are getting two separate classes from this X6 operation. So the table will be like this. Identity element 2C3, 3C2, 3 sigma V, uh, S61, S62, and I operator. So the order is 3, 6, 9, 11, 12. Order is 12, but the class number of class is equal to 1, 2, 3, 4, 5, 6, 7. This C62 is equal to C31. This C6S4 is equal to C32, which are already counted in as in this C3 class. Okay, so here we will have only one class appearing from S6. Okay, which will have two operations associated with it, that is S61 and S65. So here I am writing it as 2 S6. So we will have six classes. Okay. So let us move to our last point group, which is DNH. So what are the symmetry operations present in this point group? It has Cn as principal axis of rotation, then NC2 perpendicular to it, and sigma V planes, sigma H horizontal plane, and Sn present, and if n is even, then I will also be present. You can go back into the last lecture slides and look for these rules, which I've already mentioned there. Okay. So what are the rules associated with this point group? So the classification of Cn and Sn will be according to the usual rules which I have mentioned earlier. Okay. Classification of Cn and Sn will be according to usual rules. But classification of NC2 will be different here, which is as follows. If n is even, then it will have two classes of NC2. If n is odd, then all C2 axis of rotation will be counted in one class. And the classification of vertical planes will also be different here. Classification of n sigma v planes. So if n is even, then it will have two class of n sigma v. If n is odd, then it will have one class of n sigma v. So let us take example of D2H. The symmetry operations, it will have a C2, 2C2, 2 sigma v, sigma h, I, and E. And it will have S2 improper axis of rotation, but S2 is I only, so it won't be counted separately. So what will be the group multiplication table for it? We'll have E C2. Since n is even here, so we will have this n C2, that is 2 C2 in different classes. Similarly, for vertical planes, we will have different classes, and sigma h and I, as we know, have always different classes. So the order here is 1, 2, 3, 4, 5, 6, 7, 8. Order is 8 and class is also 8. Okay. And if we take D3H, it will have, I'm writing it directly because we have very less time left. So it will have E2C3, 3C2, 3 sigma V, sigma H, 2C3. You can practice you can practice to make a group multiplication table with by taking different molecules, finding different symmetry operations in them, and then putting and then finding it and then linking it with the point group they are associated with, and then you can also check the whether the molecule is polar or it is optically active or not, and then you can also check uh, whether the group is abelian or non-abelian, and now you can check the properties of the group: closure property, associative property, identity element, inverse rule, and for abelian groups you can check the commutative law. And now to make a group multiplication table, you can easily classify different symmetry operations into different classes and make a proper group multiplication table. Okay, so this is it for the today's session. If you have any doubts, you can write in the discussion forum, or you can also mail me on this ID, which I have been using, 2144060002 @iitb.ac.in. So thank you for your attention. Goodbye.